Okay, so this video we're going to be incorporating the pulley and friction back into the answer that we got before. Now our answer before was 208 joules of work would be required to move it 2 meters forward. But we haven't included friction or the pulley yet. So let's include friction first. So how do we find the friction? Well, if we just look at the square on its own, ignoring the pulley, we know that we can find out what friction is by using the friction coefficient and also the force directly against the triangle. So the force perpendicular to the triangle's side, I guess you could say. And multiplying this force down right against the triangle and the force and the friction coefficient will get you your friction. You can probably we haven't done any videos on the friction coefficient yet, so but Khan Academy has some great ones. So I would go on Khan Academy. Just look up friction coefficient on Khan Academy. They probably have something. Yeah, they almost definitely have something. But yeah, so just look up friction coefficient. Khan Academy is a safe place to go. So anyways, we have to find, let's just say that the friction coefficient of this is 0.5. It's just given to us. Okay, so 0.5 is our friction coefficient. So now we just need to find out what the normal force down is. Well, we know that this force directly down, right, the force directly down is going to be 15 times 9.8, right, because it's just mass times gravity. That's going to be the work going down. That's going to be the force going down. Okay, so if that's the force going down, we need to know what the force going right against the triangle is, right? Alright, so what we can find is that by using this force and then making just a triangle, this angle right here is actually going to be equal to this angle. That's a rule. You can choose to do the geometry yourself if you want, but that is a rule. Okay, now we know that this is 45 degrees, so that means that this also must be 45 degrees. So let's redraw this triangle just to make it simpler. So this is the triangle over here, by the way, that we're drawing, not this one. This triangle, the small one. Okay, now we know that this is going to be 15 times 9.8. And what we're trying to find is this right here. This is our x. So we can do cosine of 45 times 15 times 9.8, right? So let's just do that on the calculator right now. Okay. So we go 15 times 9.8 times cosine of 45. That gets us about 104. Okay, so 104 is going to be our force directly against this right here. Now notice how we had 104 last time in our last video, and don't worry if you're confused about that. That's just because the angle is 45 degrees. That's something to do with trigonometry. So the reason this is 104 has no correlation to the physics of this problem. So just because this is 104 doesn't mean that it really has any relation to the force going this way. So yeah, so this gets us 104, but that's just because the angle was 45 degrees. So that means because cosine of 45 and sine of 45 are going to be the same thing. Okay, so we have 104 is going to be our normal force, or our force right against the surface, and then we multiply that by 0.5 to get our friction. So that gets us 52. And 52 newtons will be our friction. So 52 newtons is acting backwards against the square. So let's just make a new page. And this square is going to be on this triangle. 52 newtons is going to be backwards, going against it. And how long do we have to pull this up? We have to pull this up for 2 meters, right? So overall, the amount of work that is actually being put back on that square is going to be 52 times 2, which is back to 104. So 104 joules of work are being put back on that square. That's how much more difficult it is. So what was our answer from before? 208 joules. So not only do you have to do the 208 joules to move this up, but you also have to account for all of this that's being put against it. So that means that you have to counter this friction, and you also have to push it up. So that gets us to 312 joules. Sorry, equals 312 joules. Okay. So now we know that if we were just pushing this square up 2 meters, it would take 312 joules of force. But that's not the case, right? We're using a pulley. So we have the square, and there's a pulley that's doing the work for us. Okay. Okay. So this pulley right here is going to be, well, a pulley, right, has string. And this string right here, let's say that it's length L. And this length of this string and this length of this string are going to be equal, right? So we can just call them both A. I'm just picking random variables here. So this will be A, this will be A, and this will be L. Let's just make it capital so it's clear that it's an L. Okay. So you know the amount of string in total always has to be the same, right? Because it's the same amount of string in the system, right? So, for example, if you moved L a certain distance, let's call it V. Say you moved the LV down. That means that you would have to lose V in this part of the system. But there are 2 strings. So that means that you would actually only move 1/2 V with each of them. So that means that the distance that you move here, you only see about half of it moving over here. So that means yeah. So that means that this is going to move half the distance that you pull, right? And you know force times distance is always going to be the same. And that means that force times distance, so 1/2 V is our distance, times some force, right? Let's say call it force sub 1, because this is going to have force sub 1, will equal V times force sub 2. Now if we do the math, we get 2 times force sub 2 equals force sub 1. So that means that you have to use half the amount of force to move this over here. So that means this pulley allows you to use half the amount of force that normally pushing something would cost. Okay. Now be careful here, because this could throw you off. So this pulley, it said that the force is different, but we're trying to find work. So this pulley really doesn't make a difference. It's just going to be work. So your answer is 312 joules. The pulley does not affect anything. It cannot take or add any amount of energy to the system. It was just put here to throw you off. It does change how much force you have to use, but in return for having less force, you have to have a greater distance. So it's going to be the same amount of work. So this pulley here actually doesn't make a difference. So you could basically ignore it, but because it's always going to have the same amount of work. The only difference this pulley had was it made it so that you could use less force and more distance to get this job done. But it's still 312 joules that you had to use. So our answer is 312 joules. We did have to account for friction, because friction does affect how much work you have to put in. But the pulley here was actually just put in to throw you off. So yeah, and remember, you should always have a lot of confidence in your knowledge of force and work. They are very different things, and pulley systems, they can definitely throw you off. So yeah, so that's pretty much wraps it up. Our answer is 312 joules. It will take 312 joules to move this square up 2 meters. And yeah, but the pulley was pretty much irrelevant. Okay, thank you.